This podcast covers the history of the atom and how it was discovered and highlights a few of the scientists that were involved. So we start with Dalton and his atomic theory, and he published something called A New System of Chemical Philosophy in 1808, and the basic ideas of his theory said that all matter is made of atoms, and the atoms are the smallest unit of matter. Atoms are indivisible. All atoms of the same element are identical to each other, and that atoms combine in fixed ratios to form compounds. So Dalton's theory forms the basis of what we now call atomic theory. What Dalton's theory could not answer was what is an atom made of, what's inside of it, and how do atoms combine to make compounds? What exactly are bonds and how do they form? So starred here are number 2 and 3, and these we now know are not true. So we know that atoms are not indivisible. We know that they actually are composed of smaller pieces, which we'll talk about. And we now know that all atoms of the same element are not exactly identical because we know that atoms can have various isotopes of the same element. So we're going to start with Thomson. And Thomson was British in late 1800s, and he discovered the electron by something that we called a cathode ray tube, which is the kind of tubes that are in the old-fashioned televisions. The big, huge box televisions, they have cathode ray tubes inside of them. So study of electricity showed that it is made up of charged particles. So they knew that it was charged, and And what he was able to discover was that with the cathode ray tube, this is the beam of electron particles, he could bend the ray in a magnetic field, and this shows that it was consisting of charged particles. The ray bends towards the positive plate, and because positive and negative electrons charges attract each other, they knew that the ray was consisting of negative particles. And every ray is identical for any cathode, no matter what element it was made of. So that's told them that these particles are found in all matter. And this was the electron. So what Thomson measured was the ratio of a mass of an electron to the charge of an electron. And what he found was that the mass of an electron is 1,000 times lower than its charge. So the mass of an electron was really, really, really tiny. And this was important because it showed that electrons were very, very small and very highly charged, considering their size. There's a video, it's on Schoology, the link is up there, that talks about Thomson's cathode ray tube and how he discovered the electron. So here's a diagram of the tube. Here's the ray, and here they can show that it bends back and forth based on a magnet placed next to it, positively charged metal plate, and it is deflected towards that plate, and it's deflected away from the negatively charged plate. So then Millikan came along, and he was American, turn of the century, 1900, and he was able to take what Thomson had done and use it and do experiments to determine the exact mass of an electron. And we call his experiment the oil drop experiment. And the way it was set up was it was in a drum where he vaporized really, really tiny particles of oil, super, super small, sprayed into a charged plate, and then what he was able to do was adjust the rate at which the oil drops fell by changing the charge on the plate. So what this was able to do, Thomson had already done the mass to charge ratio. And Millikan was able to figure out what charge it required to stop the particles from falling, and he was able to use that to figure out the mass of an electron. And we're not going to repeat the math here, except to say, here's a copy, a summary of his work, and 9.1 times 10 to the minus 28 grams. So all we are going to take from that is that it is really, really, really small. Super small electrons. Again, there's a video on Schoology, the link is there, that talks about Millikan's oil drop experiment. Stop now and go and look at the video and then come back. Okay, so next came along Rutherford, and Rutherford was also British, early 1900s, around 1910. So now at this point, scientists knew that there were 3 subatomic particles in an atom, and they were protons, electrons, and neutrons. And they knew that protons were positive, and electrons were negative, and neutrons were neutral. But what they did not know was how they were arranged, and this is what they thought. We call this model now the plum pudding model, and I'm not sure if they called it that. But what they thought was that particles were distributed evenly throughout the atom. So this is a model of their atom. The protons are positive, the little pluses. The electrons are negative, the little minuses. The neutrons are neutral, those are the zeros. And they assumed that everything was spread out evenly, which totally makes sense because we know that positive and negative particles are going to be attracted to each other. So it makes sense that they would be totally spread out evenly. So Rutherford designed an experiment that we call the gold foil experiment, and this is a diagram of how it works. So he has a beam of alpha particles coming through here, and they are shined on this really, really thin piece of gold foil, like gold leaf, super, super thin, so that it is only a few atoms thick. So this is like a model of the gold foil, and these circles here are like the gold atoms. And the alpha particle beam would come straight through, and then hit the foil. And then after it hits the foil, it would then be detected by this detector that comes around the edges. That's a picture of his experiment. And so the hypothesis was what he expected based on the plum pudding model of the atom. He thought that particles would be deflected through the gold foil. So they would come in, hit the gold foil, and then they would go through, but the gold foil would cause them to be deflected, and then they would be registered by the detector. What the actual results were incredibly shocking to Rutherford and his group. And what happened was the alpha particle came in, it hit the gold foil, and most particles, 99%, went straight through as if nothing was there. No deflection, straight through. And then a few of them, a small percentage of them, were deflected, but they were deflected a lot. Some of them even bounced back in the other direction. And the story goes that this would be as if you shot a gun at a piece of tissue paper, and every once in a while the bullet would bounce off the tissue paper and go straight back where it came from. So it was incredibly shocking because the foil was so very thin. Again, there's a video, the link is in Schoology, talking about Rutherford's gold foil experiment. And you should look at that. You should watch that video. So what this showed was an atom is mostly empty space. That's why the particles mostly went straight through as if it was empty. But the atom has a super small, tiny nucleus in the middle that is positively charged. And that's why the alpha particles were deflected, because every once in a while they would hit an atom and hit the nucleus. And because the alpha beam was positive and the nucleus was positive, that's what caused it to bounce off and deflect.